This video is a continuation of the video entitled Cloud and Data Metamorphosis Part 1, which is the third video, a multi-video series, in the larger video series entitled AI, ML, and Advanced Analytics on AWS. Let's quickly overview Part 1 of Cloud and Data Metamorphosis and quickly introduce you to the topics in this Part 2 of Cloud and Data Metamorphosis. In Part 1 of Cloud and Data Metamorphosis, I covered the following: Big Data Evolution, Cloud Services Evolution, Database Evolution, and the many types of AWS's purpose-built databases, polyglot persistence, the differences between traditional and cloud application characteristics, and how to determine if your database is operational or analytical. In Part 2, I'll cover amazing data factoids that impact analytical systems, Analytical Platform Evolution, dark data, the problems with data silos, data architecture evolution, and modern distributed data pipelines. First, we'll cover amazing data factoids. I'm sure you know that there is so much more data than most people think. Today, however, we have more ways to analyze data than ever before. 11 years ago, Hadoop was the data king of analysis. 8 years ago, Elasticsearch was the data king of analysis. 5 years ago, Presto was the data king of analysis. Less than 4 years ago, Spark was the data king of analysis. Today, AI is the data king of analysis. With the democratization of data, there are more people working with data than ever before. Job titles that never used data before must use it now to analyze performance, for reports, and more. The old adage, garbage in, garbage out, carries more weight today than ever before. Organizations gather huge volumes of data, which, they believe, will help improve their products and services. For example, a company may collect data on how users use its products, internal statistics about software development processes, and website visits. However, a large portion of the collected data are never even analyzed. According to the International Data Corporation, or IDC, a provider of market intelligence on technology, 90% of the unstructured data are never analyzed. Such data is known as dark data. Dark data is a subset of big data, but it constitutes the biggest portion of the total volume of big data collected by organizations in a year. Dark data are the information assets organizations collect, process, and store during regular business activities, but generally fail to be used for other purposes like analytics, business relationships, and direct monetization. The graph shown on this slide illustrates that as the amount of big data grows, the amount of dark data increases. But that doesn't lessen its importance in the context of business value. There are two ways to view the importance of dark data. One view is that unanalyzed data contains undiscovered, important insights and represents an opportunity lost, whether today or in the future. The other view is that unanalyzed data, if not handled well, can result in a lot of problems, such as legal and security problems, like with the recent GDPR laws and more. Just storing the data isn't enough. Data needs to be discoverable, and I'll be showing you how to do that in this video series. With the varied types and new sources of data are added to an analytical platform, it's important that the platform is able to keep up. This means the system has to be flexible enough to adapt to changing data types and volumes. In the remainder of this video and throughout the next videos, I'll explain the technologies that not only makes data discoverable, available to numerous analytical and AI services, cleans and enriches your data, but also future-proofs your data. This quote is from Atul Butte, who has an MD from Brown University, a PhD in health sciences and technology from MIT and Harvard Medical School, and is the founder of Butte Labs, solving problems in genomic medicine. It reads, "Hiding within those mounds of data is knowledge that could change the life of a patient or change the world." Analytical systems are only as good as the data used to power it. Believe it or not, most people have dirty data, meaning not only incorrect data, but missing data, duplicate data, and incomplete data augmentation. A robust analytics platform is critical for an organization's success. Dirty data can derail analytical projects completely. In addition, most organizations struggle with having complete data for analysis because of the difficulty, the complexity, the laborious and time-consuming task of bringing the data they need for complete and accurate analysis from many disparate data silos scattered across the globe in differing formats and proprietary systems. These organizations have been forced to use different systems at different stages of growth because there really wasn't a solution, much less an elegant solution, to have all the scattered data silos in one place, until now, which will be covered in this series. The data silo effect is amplified by vendor lock-in and the immense amount of work required to transform legacy data systems to work with current data systems. Just like there's big data and cloud evolution, there's also data architecture evolution. So let's dive in. Finding value in data is a total journey and is often painstakingly undertaken with data silos using a plethora of tools. Data silos are a chronic, deep-rooted problem companies face on a daily basis. Some of the problems data silos create are the following. The contents of data silos will likely differ slightly. It's difficult to determine which one is the most accurate or up-to-date. Data silos cause wasted resources and inhibited productivity. Different tools and interfaces used to do jobs isn't in a consistent manner, having unpredictable and sometimes disastrous results. Many situations occur where separate teams could use another team's data to solve problems more efficiently if they had access to it. It's difficult to move data across silos. With multiple people and teams working on the same data, you're forced to keep multiple copies of the data. Getting the right data from data silos is extremely complex, often abandoned, doing analysis on a subset of the data, resulting in incorrect and incomplete analytical insights. Having consistent data transformation and data governance through all silos borders on impossible, depending on what type of storage each silo has. Users struggle to find the data they need because finding data stored in a siloed architecture is akin to looking for a needle in a haystack. These factors and more slow innovation and evolution drastically. It's expensive not only to move the data, but to pay for many different silo services, and in all probability adds up to paying for storage you don't need today. Many companies don't have all these silos mapped out, and if they do, paying employees to keep up legacy systems is a waste of their time, their talents, and preventing them from working on more important tasks like innovating, experimentation, and building great products. There has to be a better way to deal with siloed data. Well, there is. And I can't wait to explain it to you, starting in the remainder of this video and extending to the next video. This diagram shows the challenges data teams face today. With the exponential growth of data from many and varied data sources, the older systems weren't designed to handle the volume, variety, velocity, and the veracity or accuracy of the data. Data is now ubiquitous. Almost every employee has to work with data, but oftentimes in different ways on the same data, increasing the complexity of the data while increasing the chance of data errors. And with the explosion of the many ways to access the data, most people have their tool of choice. And moreover, certain job roles necessitated working with particular access mechanisms. The reason we create applications is to deliver business value, delivered by creating business logic and operating it so it can provide a service to others. The time between creating business logic and providing service to users with that logic is the time to value. The cost of providing that value is the cost of creation plus the cost of delivery. As technology has progressed over the last decade, we've seen an evolution from monolithic applications to microservices and are now seeing the rise of serverless event-driven functions led by AWS Lambda. What factors have driven this evolution? The answers are the following. Low latency messaging enabled the move from monoliths to microservices. Low latency provisioning enabled the move to Lambda. Monolithic means composed all in one place. A monolithic application describes a single-tiered software application in which different components are combined into a single program from a single platform. The diagram on this slide is a sample e-commerce application. Despite having different components, modules, and services, the app is built and deployed as one application for all platforms, such as desktop, mobile, and tablet, using relational database services as the data source. The drawbacks of this architecture include apps can get so large and complex that it's challenging to make changes fast and properly. The size of the app can slow down startup time. With each update, no matter how small it is, you have to redeploy the entire app. It's very challenging to scale. A bug in any module can bring down the entire app because everything for the app is connected together. It's very difficult to adopt new and advanced technologies. And if you try to do that, you have to pretty much rebuild the app, which is costly, takes a lot of time, and a ton of effort. The conceptual image on this slide provides a representation of breaking a monolithic application into microservices. In monolithic architectures, all processes are tightly coupled and run as a single service. With a microservices architecture, an application is built as independent components that run each application process as a service. These services communicate via a well-defined interface using lightweight APIs. Services are built for business capabilities, and each service performs a single function. Because they are independently run, each service can be updated, deployed, and scaled to meet demand for specific functions of an application. Characteristics of microservices include the following. Microservices are autonomous. Each component service can be developed, deployed, operated, and scaled without affecting the other functioning of the other services. Microservices are specialized. Each service is designed for a set of capabilities and focuses on solving a specific problem. Microservices have great agility. Microservices foster an organization of small, independent teams that take ownership of their services. Teams act within a small and well-understood context and are empowered to work more independently and more quickly. This shortens development cycle times. You benefit significantly from the aggregate throughput of the organization. Microservices have flexible scaling. They allow each service to be independently scaled to meet the demand for the application feature it supports. This enables teams to right-size infrastructure needs, accurately measure the cost of a feature, and maintain availability if a service experiences a spike in demand. It's easy to deploy microservices. Microservices enable continuous integration and continuous delivery, making it easy to try out new ideas and to roll back if something doesn't work. Microservices allow technical freedom. Microservices architectures don't follow a one-size-fits-all approach. Teams have the freedom to choose the best tool to solve their specific problems. With microservices, the code is reusable. A service written for a certain function can be used as a building block for another feature. This allows an application to bootstrap off itself, as developers can create new capabilities without writing code from scratch. Microservices are resilient. Service independence increases an application's resistance to failure. Applications handle total service failure by degrading functionality and not crashing the entire application. On this slide is the e-commerce diagram redrawn from the previous slide to represent a modular microservices architecture consisting of several components or modules. Each module supports a specific business goal and uses a simple, well-defined interface to communicate with other sets of services. Instead of sharing a single database, as in a monolithic application, each microservice has its own database. Having a database per service is essential if you want to benefit from microservices because it ensures loose coupling. Moreover, a service can use a type of database that's best suited to its needs. The benefits of a microservice architecture includes continuous delivery and deployment of large, complex apps. Services are smaller and faster to test. Services can be deployed independently. It enables you to organize the development effort around multiple teams. Each team is responsible for one or more single service. Each microservice is relatively small. It's easier for developers to understand. The IDE is faster, making developers more productive. There's a faster startup time. It has improved fault isolation. If one service has a bug, it doesn't affect the other services. And it eliminates any long-term commitment to a technology stack. When developing a new service, you can pick a new technology stack. Similarly, when making major changes to an existing service, you can rewrite it using a new technology stack. The architectural drawing on this slide is an example of modern data architecture. You'll notice an abundance of data sources in the far left column surrounded by the blue rectangle. These represent a good sample of the wide variety of data sources today. Moving to the next column, surrounded by a red rectangle, the services shown represent a good sample of the many different ways to ingest data into AWS. Which service you use depends on several factors, such as if the data is streaming in or not, how the data is migrated in, if you have a hybrid cloud environment, and more. The next section is the storage section. Notice there are two separate storage sections. One on the bottom, surrounded by a blue rectangle, which represents data that's streaming in, pointed to by the blue arrow. And the top section is surrounded by a green rectangle that represents slow-moving or batch data. In the streaming section, Amazon Kinesis Data Streams is streaming in data, shown in both the ingestion section and the streaming storage section, surrounded by red rectangles and pointed to by red arrows. The Kinesis event capture in the streaming storage section captures the streaming data as it flows into AWS. In this particular architecture, the Kinesis event capture passes the ingested data to Amazon EMR, or Elastic MapReduce, to perform some initial stream processing, shown surrounded by a blue rectangle and pointed to by another blue arrow. When the initial processing is complete, the streamed-in data is put into an Amazon S3 raw zone bucket, surrounded by an orange rectangle and pointed to by an orange arrow. If the data wasn't streaming data and it was slow-moving data instead, then, rather than Amazon Kinesis data streams, the data would be put into the Amazon S3 raw zone bucket by Amazon Kinesis Data Firehose, although this diagram doesn't show that. Whenever any further processing needs to be performed, the data in the S3 raw zone is acted upon by whatever the processing service is, shown in this diagram as Amazon EMR's mlib performing ETL, surrounded by the green rectangle and pointed to by a green arrow. Amazon EMR's mlib is one of Amazon's built-in Apache Spark machine learning tools. The results of EMR's ML processing is placed into an Amazon S3 processed zone bucket surrounded by an orange rectangle and pointed to by an orange arrow. Amazon S3 processed zone buckets is where the data is staged in an Amazon S3 data lake, where it awaits any downstream requests to use that curated data. Surrounded by a pink rectangle and pointed to by a pink arrow is a sample of the AWS data stores that serve the data to consumers. The job roles, surrounded by a yellow rectangle and pointed to by a yellow arrow, shows the typical job roles next to the type of services work with that type of data. On the top right, you'll see AWS services that are commonly used in a modern cloud data architecture, surrounded by a purple rectangle and pointed to by a purple arrow. Notice how all data, no matter if it comes streaming in or comes in moving slowly, eventually ends up in an Amazon S3 raw zone bucket. And after some initial processing to prepare the raw data for downstream consumption, ends up in an Amazon S3 processed zone bucket. I'll elaborate on those two S3 storage locations in the next video. Let's now look at how modern data analytics pipelines are built today. Modern analytical data pipelines decouple storage from compute and processing. In this manner, when a newer technology is introduced, it's much easier to swap out a storage or compute service for another one in the same category. Modern data pipelines have many iterations of processing and analyzing and storage. Pipelines can go off in multiple directions, depending on what downstream applications will be doing with the processed data. What you're looking at on this slide is a simplified architectural diagram to emphasize that both batch and real-time processing can occur at the same time and even have dozens and dozens of threads being simultaneously processed within each. The point is to see that multiple strings of analytics can be performed simultaneously on the same data set, shown here as a batch workflow and a real-time streaming workflow, when you use 3 key AWS services: Amazon S3, AWS Glue, and Amazon Athena, that I'll be introducing shortly. The really cool thing about this is that using these technologies that I'll soon be describing, there's no limit on how many concurrent users that can work on the same data sets without affecting the underlying data source, no matter where in the world it's stored. In the next section of video number 3, Cloud and Data Metamorphosis, I'll cover the following: Cloud Services Evolution, Serverless Architectures, AWS Lambda, and everything you need to know about containers. See you there!